Hello, ladies and gentlemen. Thank you for joining me. I'd like to thank my co-authors, Richard Perez at SUNY Albany and Tom Hoff at Clean Power Research. I'm Dr. Mark Perez, lead researcher at Clean Power Research. Today, I'll be speaking about where and how much, the land use implications for high penetration PV. Some of the motivations for this work all revolve around addressing misconceptions. Firstly, and this is a misconception that we and other authors have responded to many times already, can solar power almost everything? Secondly, the 24-365 question. What do we do when the sun doesn't shine? We'd like to primarily focus on where to deploy in the context of electrifying everything, both transport and heating. Is there enough land available in order to support the renewables development that we need to meet all of our energy needs after we electrify everything? We take two approaches to addressing this question, top-down and a bottom-up approach. There is a lot of high-tech science underlying this work, but I'll try to keep the results and description of the analyses that we've done at a very high level in order to be understandable by as many people as possible. So here are some recent news articles. Energy sprawl in the green economy, developers under fire, solar farm moves closer to approval, US will need a lot of land, cropland eaten up by solar. This is just a handful of recent articles from major news sources. But I'm only scratching the surface here. You may have seen some yourself. Hopefully, we address these misconceptions in this talk, and we provide actionable information that will help you, the listeners, succinctly respond to them. So first, this big misconception is, are the renewables big enough? You may have seen this image before. The volume of each sphere corresponds to the amount of energy available. The global primary energy consumption is over in the bottom left corner, 19 terawatt years per year. The finite resources are over on the right. These are the reasonably assured recoverable reserves. If we were to extract all of them, burn them, or fission them. Over on the left, we have the annual renewable flux. And as you can see, solar, as most of you know, is roughly 1,200 times the size of the global primary energy consumption annually. So there's plenty of solar to go around. And there's plenty of wind. Even if we just constrain ourselves to solar and wind, there's plenty to meet global primary energy demand now and well into the future. The 24-365 question. How do we transform this signal, which is 1 day of PV production at a single site in New York State? And here you can see the diurnality of the resource, the rising and setting of the sun, and the effect of clouds. This is at the 1 minute interval, so you can see very noisy. This is an intermittent signal. How do we transition this into something that can firmly meet load 24/7? This is the load curve for one of the NYISO zones, one of the large TSOs in the US. How do we address things like the duck curve? As we start to add more unconstrained PV into the equation, you see this famous duck-shaped curve take effect. And you see this in Germany, you see this in California, everywhere there's a lot of PV. How do we address this? This is the intraday perspective, but perhaps more importantly from an energy balance standpoint is the multi-day or seasonal perspective. How do we take this noisy annual signal, this is daily interval PV over on the left, and daily interval load on the right for the same place, for the same location. How do we balance these two? Because the curve on the left looks very different from the curve on the right. How do we account for things, very low yield periods like this in the winter, pictured here and encircled in yellow? How do we do it? Well, the first thing that comes to mind is energy storage, of course. You could use fuel or something like that to burn during times of deficit, but we can also use energy storage in a carbon neutral standpoint, charging in times of excess and discharging in times of deficit. But it costs a lot of money. With unconstrained PV costs roughly 2 cents per kilowatt hour in the future in this region that we studied. Firm PV kilowatt hour costs almost 20 cents per kilowatt hour, and that margin is the cost contribution of storage. You need a lot of storage in order to balance the equation, and that's largely linked to, at least in this particular case, the seasonal imbalance. Enter oversupply and curtailment. As you start to overbuild the PV, you start to increase yield in low yield periods, like the winter, and therefore you decrease the amount of storage you need, but of course you increase the amount of PV. But there's a balancing point that balances these two cost equations. There's a sweet spot. It's the affordability sweet spot, we're calling it. And in most of the regions we've studied, it's at roughly 50% overbuild on capacity. This is so effective at balancing that we're calling it implicit storage, because it's nearly as effective as regular energy storage. A lot of articles written on this in recent history. Here's a Quartz article. Solar energy is so cheap it can be wasted. This Minnesota Solar Pathway study, where we really advanced the science on this work, we discovered that from a cost optimal perspective, we have roughly 55% PV, 40% wind, 5% legacy natural gas for balancing, with an optimum renewable overbuild of 50%. So we're going to apply these same percentages throughout the rest of the US, even though as you go further south, there's probably less overbuild needed and probably a little bit more PV in the equation because of the seasonal imbalance dynamics. This is, we're talking about the northern region right here. We take a three-step process. First, how much energy do we need? We calculate future energy use in the advent of transportation and building electrification. And then we calculate how much land do we need. We assess land use for PV when it's meeting 55% of all load, in the same manner in which we did for the Minnesota Solar Pathway study. Finally, we ask the question, where do we deploy? Where do we actually site the PV? So first, how much energy do we need? This is the US picture. We have 4,000 terawatt hours of annual electrical demand. If we electrify terrestrial transportation, all of it, we roughly increase that by 50%, 2,000 terawatt hours. And then if we electrify residential and commercial buildings, we add another 1,000 terawatt hours roughly. So all in all, 7,000 terawatt hours. New York State, it's roughly the same ratio. There's a little bit more heating demand on a relative basis because it's further north than the US on average. So there's a little bit more heating demand to be electrified. In New York, it's 330 terawatt hours. So on the supply side, what do we need for this? We need 189 gigawatts of PV. And here we've broken it down by sector. This is to meet 55% of this load, as mentioned before. The other 45% coming from mainly wind. This corresponds to about 360 square miles of land use. And multiply this by 2.5 to get to square kilometers for all you Europeans in the audience. We take two approaches to answer the question where to deploy. First is a top-down approach. By comparing with existing land cover archetypes using the National Land Cover Database. And secondly is a bottom-up approach, a comparison with existing land cover using detailed GIS info. So first, this top-down approach. So in order to meet this 360 square miles, let's look at the existing land use breakdown. Here it is in New York State. We have roughly 25 to 27,000 square miles of forest, and then smaller amounts of hay pasture, cultivated crops, wetlands, etc. down the line. To put it into perspective, look at this little yellow piece within the bottom of the question mark. This is 360 square miles. So it might seem a lot when contiguous, but when compared with the existing land use, it's very minimal. We assign percentages to these different land cover categories, 15% for urban. So we're saying 15% of urban real estate is available for PV deployment. We say 5% of suburban sprawl is available, 5% of open water, floating PV, 1% of cropland, agrivoltaic, 1% of hay pasture, also agrivoltaic, etc. This comes out to 650 square miles if you've taken our subjective allocations to heart. And just to show how small this is in a relative basis, I've highlighted the amount of land covered by forest in New York State in the 1880s. So we've really reforested a good chunk of the state. So even if we add, this is what 650 square miles looks like, on the margin here. It's very small relative to the amount of reforested land as we've moved away from agriculture in the state. So it's a small amount, so 650 plus plus. We could add quite a bit more if we needed to. Then we take a bottom-up approach. This is the end-use activity standpoint, deploying PV without functional modification. So we have buildings pictured here, commercial, industrial, residential. If we say 50% of all buildings can be covered with PV, that comes up to 185 square miles. Power lines, rights of way, pictured here. Here we have a shapefile of all of the various voltages of power lines in the state of New York. If we say 75% of the right of ways pictured at bottom left here are covered with PV, 161 square miles available. Gas pipelines, the same thing, 75% right of way utilization, 21 square miles. Railroads, 21 square miles. Expressways, 12 square miles. Vehicle integrated PV, there's a lot of real estate on these large trucks on the containers, or on the vehicles themselves. There's a Fisker Karma and a Peugeot with PV integrated into the roof. If we do 50% surface utilization of vehicles, that's 21 square miles. Of course, they need to be parked in the sun, primarily during the day. Then we have landfills, industrial, mining, exclusion zones. If we add all of that up, 50% of the land use, that's 29 square miles. And then we have parking lots, 50% of parking lots covered with PV, 24 square miles. If we add all this up, it comes out to 476 square miles with minor modification of function. Now, of course, you have agrivoltaic, floating PV, and we can expand the right of way marginally to chop back a little bit of forest to come back to the forest question. So it could be much more. So 189 gigawatts of PV required to meet all primary energy demand in New York State, 360 square miles, 650 square miles from the grand occupancy standpoint, and 475 square miles from the end-use activity standpoint. There's room to grow, clearly. With higher efficiency PV, demand-side energy efficiency, these numbers can only go down, and the land use can only go down. So there's plenty of room to grow. We ran this analysis for every state in the continental United States, and pictured here is the room to grow calculated in the same manner for every state. It's a heat map, so the areas with more room to grow, like the Dakotas and Montana, Idaho, these areas have a very low energy use and a very high surface area of available area for PV deployment. So there's plenty of room to grow in those states. There's a little bit less on the East Coast, which are more dense, less urban area, that we've included. So New York State, we've run the analysis, and if you want to, we have a Solar Energy Journal article that has come out, and we also have an interactive web app where you can select the state of interest and change these assumptions for percentages of usage of these different land cover categories. You could say, I want 80% of urban land use to be able to be covered by PV. How does that change the total available land area relative to how much we need and the room to grow, etc. So you can change all those assumptions. We've also run it for the entire US. Here's the breakdown of land use in the United States. As you can see, unlike New York State, most of the United States is scrub/herbaceous land cover. But there's 373% room to grow using the assumptions we've come up with in the paper. So check out our web app, check out the Solar Energy Journal article for more details on this. And here's just a screenshot of the web app. You can even change the percentage of load met by PV over here with this slider. Here we've assumed 55%, but you can say, what does it look like for land use perspective if we want to meet 100% of load in Alabama with PV alone? What happens if we increase the efficiency of PV? How does that change the perspective? If you want to dive into the rooftop analysis a little bit more, check out the Solar City Simulator at IRENA. This is a tool we've been collaborating on in conjunction with IRENA, where you can calculate the rooftop PV potential for any building within any of these cities listed here, and this list is continually growing. So thank you very much for your attention.